In the penultimate section of this chapter, we're going to be looking at linear systems with complex eigenvalues. So far in section 10.4, we looked at solutions to linear systems of ordinary differential equations with distinct real eigenvalues. And we have looked in section 10.5 at linear systems with repeated real eigenvalues. So the only type of system we haven't looked at yet is the one we're looking at in section 10.6, which is our linear systems with complex eigenvalues. And we're going to find out we handle them in a somewhat similar way, but it's going to be a slight bit more complicated because we have to deal with the real part of our eigenvalue and the complex part. So if we look at this particular homogeneous system, we have a y prime is equal to the coefficient matrix negative 1 half 1, negative 1, negative 1 half times y. Our characteristic equation, and again, remember that's a minus lambda I. So we're looking, there we go. There we're looking at negative 1 half minus lambda and 1, and then negative 1 and negative 1 half minus lambda. So if we look at our characteristic equation that's related to the system, we end up with lambda squared plus lambda plus 5/4 equals 0. And when we use our quadratic formula, we find out that lambda is negative 1 half plus or minus I. So remember, that's in the form of alpha plus or minus beta I, right? So we talked about that before. And alpha and beta are real valued numbers, but the beta I term is our complex portion of our eigenvalue. So once we find these two eigenvalues that are complex, we talked about how to find complex eigenvectors associated with complex eigenvalues. And we found out that we have eigenvectors. Our first eigenvector is 1 and I. Our second is 1 and negative I. So these eigenvalues and eigenvectors then lead us to our two solutions. The first one being 1i, the vector, times e to the negative 1 half plus I times t, and y2 being 1 negative I e to the negative 1 half minus I times t. So to obtain our real valued solutions, then we're just going to use Euler's formula again. And then our following theorem that says to consider the system, x prime is equal to p of t times x, where each element of p is a real valued continuous function. If x equals u of t plus I times v of t, in other words, if u is the real part and v is the imaginary part, right? And that is a complex valued solution of our equation, then its real part, u of t, and its imaginary part, v of t, are also solutions of this equation. So in other words, what we're going to do is once we put these together, we are going to separate the real valued part from the complex part, and then we will simply factor out of everything the I on the complex part, and we'll bring it outside of our vector and find that what is left is our v of t, or our second solution, y2. So we will have a real valued solution, and then we will take the real valued part of the complex part of the solution, and that will also be a solution. What does this look like? Well, let's look at this exact same problem. So we can choose the real and imaginary parts of either y1 or y2 to get started. So if we look at y1, and we have 1 and I, that vector, times e to the negative t over 2, times cosine t plus I sine t. And again, this was using Euler's formula that we got there. We've done that several times. Then we can distribute and separate them out. So we would take 1 times e to the negative t over 2 times cosine t. So that's this guy. Plus 1i times e to the negative t over 2 sine t. And that's this part. And notice the I is on the outside. And now here we'll have I times e to the negative t over 2 cosine t. So now that goes to the second part of this simplification over here because it has the I. And then we have I times e to the negative t over 2 times I sine t. And this is where it's good to remember that I squared is negative 1. So when we do that I squared, we get negative 1 times e to the negative t over 2 sine t, and that's what we find here. So what we're really looking at is the real valued part of our solution and the complex valued part of our solution. And what we say is this is our u of t, and this is our v of t. And this would be y1, and this would be y2. So we would have u being, if we took the e to the negative t over 2 to the outside, we'd have cosine t and negative sine t inside our u. And then in our v vector, we'd have sine t and cosine t with e to the negative t over 2 on the outside. So that is our y1 and our y2 respectively. So we would have c1 y1 plus c2 y2. So this is y1, and this guy is y2. And here we have c1 y1 plus c2 y2. And that is equal to our function y. That is our solution to this system. We're going to look at 3 example problems, and you can follow along in your notes. Let's start with example 1. This says find the general solution of y prime is equal to the coefficient matrix 4, negative 5, 5, and this is supposed to be a negative 2. So if the notes posted online still have that as a positive 2, please change it to a negative 2. And all of this is times y. So where do we begin? In the same place as usual. We need to find our eigenvalues. So a minus lambda I, find the determinant, right? 4 minus lambda, negative 5, 5, and negative 2 minus lambda. So our characteristic equation becomes 4 minus lambda times negative 2 minus lambda plus 25. So negative 8 plus 2 lambda minus 4 lambda plus lambda squared plus 25 equals 0. Or lambda squared minus 2 lambda plus 17 equals 0. So this is when we start trying to factor things, right? What multiplies to give me 17 and adds to give me negative 2? Nothing, right? The only factors of 17 are 1 and 17. They certainly do not add up to 2 in any sense of the word. So this is one where we have to use the quadratic formula. So let's see if we can find out what lambda is. So negative b, so positive 2, plus or minus the square root of b squared, so negative 2 squared, minus 4 times a times c, all over 2a. Or we get a lambda of 2 plus or minus the root of 4, right, minus 4 times 17, which happens to be 68. So 4 minus 68 square root all over 2, or we end up with 2 plus or minus 8i all over 2. Our lambda here is 1 plus or minus 4i. And so we only have to choose one of these eigenvalues to help us find a single eigenvector. So let's do that next. Let's take, right here, we're going to find one of our eigenvectors, and you don't have to find both, you only have to find one based on the theorem that we used. So let's find our eigenvector. I'm going to use lambda 1, which is 1 plus 4i. And let's see what this looks like. So a minus lambda 1i, right? So we end up with, we have 4 minus this 1 plus 4i. In the second row, we have a 5. I'm going to go ahead and write the second row, second column expression because it's negative 2 minus our 1 plus 4i so that I can write the -5 with a correct spacing. Okay. And then it's equal to our 0 vector or augmented matrix. So if we simplify things a little bit, 4 minus 1 is 3, minus a plus is a minus, so 3 minus 4i, and 5. And then we have -5, and -2 minus 1 is -3, and then minus 4i. And again, we have an augmented matrix. It is now equal to 0. So we can take either row here and use it to help us figure out the relationship between x1 and x2. And this is, I kind of hinted at this in class, this is going to be a quicker way for us to get to our eigenvector than if we tried to figure out what to multiply the first row by in order to cancel out everything in the second row, because it gets much more complicated when you start dealing with complex numbers. So what we can say then is, so 3 minus 4i times x1 minus 5x2 equals 0. Or 3 minus 4i x1 is equal to 5x2. And this is the trick here. So we need to find a way to make these two sides equal. So if x1 is 5, then I have 3 minus 4i times 5. On the other side, I already have a 5, so x2 has to be the other factor there, which would be 3 minus 4i. Or our eigenvector would be 5 and 3 minus 4i. So again, what we're trying to do is find a way to get x1 and x2 to be equal to one another. So if we let x1 be 5 and let x2 be 3 minus 4i, then these two expressions on both sides of the equals sign are equivalent. They're the same thing. So then we have our eigenvector of 5 and 3 minus 4i. Now we could also have done it the other way with the other eigenvalue, and we would have come down to 5x1 minus the quantity 3 plus 4i all times x2, which equals 0, and you end up with an eigenvector that's 3 plus 4i and 5. So it's very similar to this one, it's just flip-flopped, and it has a different sign on the complex part of the eigenvalue. So what we're going to do then is now we're going to take all of this and we're going to put it together in step 3, where we're going to find our solution. All right, we're going to find our solution, which is y being u, right, plus vi. Right, C1u, I should say, I forgot the C1. C1u plus C2 times v. So let's see what happens. So if that's the case, then we've got a minus lambda I, right? And so what we have to look at now is we have to say y1, we're going to use our current eigenvector and our current eigenvalue and say this is going to be 5 and 3 minus 4i times e to the 1 plus 4i times t, which, using Euler's formula, says that this is 5 and 3 minus 4i times e to the t times cosine 4t plus I sine 4t. Right? Comes back to our Euler's equation. And now if we were to multiply things through, I have to say I'm going to leave the e to the t on the outside because it just makes things a little bit easier. We would end up with just distributing the 5 times the cosine and I sine and 3 minus 4i times the cosine plus I sine. And we'll just leave the e to the t on the outside because it's going to stay the same for all of them. So we would have 5 cosine of 4t plus 5i sine of 4t. And in the second entry in our second row here of our vector, we're going to have to use distribution. So 3 times cosine 4t plus 3 times I sine of 4t, right? Minus 4i cosine of 4t. And then now we have minus 4i squared, right? And it's squared because we already had an I, and now we have another one. And that would be our sine of 4t. And all of this is still times e to the t. So we end up with let's see if we can put all of our stuff together. Let's see here. We would have, let's put all of our real stuff first and then all of our complex stuff second. So we have 5 cosine of 4t, and then we'd have 3 cosine 4t, and then it would be plus 4 sine of 4t. And that came from right here. Because remember, I squared is a negative 1. So negative 4 times negative 1 is positive 4 sine of 4t. Here's our other real part. Here's our real part. So there's the real part. And then we'll also have the imaginary part. And what I'm going to say for these ones is, let's just factor out the I while we're at it. So I times 5 sine of 4t, right? And I times 3 sine of 4t minus 4 cosine of 4t. And all of this is times e to the t. And in order to get our general solution then, what we're going to do is we're going to separate out the real part and the complex part. The real part is the part that we've got here in the yellow, right? That's all of our real part. And then we also have a complex portion, which is everything with the I. It's all of this stuff. And so what we're going to do is we're just going to separate them out. We're going to say that this is the real portion, which is 5 cosine of 4t and 3 cosine 4t plus 4 sine of 4t, all times e to the t. And then we have plus, and then we would have the I times 5 sine of 4t and 3 sine of 4t minus 4 cosine of 4t e to the t. This is our u, which is y1. This is our v, which is y2. So our general solution is that y is c1, right, e to the t, I'll just put that with it, and 5 cosine 4t, and 3 cosine of 4t, plus 4 sine of 4t, plus c2 e to the t, And then we have our 5 sine of 4t, and we have our 3 sine of 4t minus 4 cosine of 4t. And that is our general solution, which probably sounds a little bit complicated, but it gets easier the more we do it. So we'll probably speed up a little on the last 2 examples. All right, let's try example number 2. It says, find the general solution of y prime is equal to the coefficient matrix negative 14, 39, negative 6, 16 times y. And this one does not have any typos on it, like the last one did. So we are going to just do this one the way it is. So let's look at it. So we want to find the general solution here. So first things first, we have to find our eigenvalues. And we know they're going to be complex because of this section. Let's see what we get. We have negative 14 minus lambda, and we'll have 16 minus lambda on the other part of the diagonal, and then let's fill in our 39 and our negative 6. Which means our characteristic equation is negative 14 minus lambda times 16 minus lambda plus 6 times 39. And we want it to equal 0. And so when we put all this together, we get a negative 224 minus 16 lambda plus 14 lambda plus lambda squared and plus 234. So lambda squared minus 2 lambda plus 10. Nothing that multiplies to give us 10 is going to add to give us negative 2. If it was subtraction, we could do a little bit of something, but not really. Even that wouldn't be 5 minus 2 would be 3, so even that wouldn't work. So we have no option but to use the quadratic formula here. So lambda is 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 10. All over 2 times 1. Or lambda then is 1 plus or minus, that's 36, so it's 6i. Or negative 36, it's plus or minus 6i, which would be divided by 2 is 3i. So we end up with lambda of 1 plus or minus 3i. So step 2 then is to find the corresponding eigenvector for either one of those eigenvalues. So you can use whichever one you want. There's values instead of vectors. So you can use whichever one you want. I tend to always use the positive one. So it's totally up to you whether you want to do the positive one or the negative one. But I'm going to do 1 plus 3i. So if that's the case, then I end up with negative 14 minus 1 plus 3i and negative 6. And this will be 16 minus 1 plus 3i. And this guy will be 39, augmented to equal 0, 0, because we want them to be linearly dependent. So if we do a little simplification here, we end up with negative 15 minus 3i, 39, 0. And negative 6, 15 minus 3i, and 0. I'm going to use the second row here this time because you could use the first row and you'll still get a very similar answer. It's just that if we use the second row, it's a little clearer that we're going to be able to factor a negative 3 out of everything. So we would end up with negative 6x1 plus 15 minus 3i times x2, or 15 minus 3i times x2 is equal to 6x1. Scroll just a little here. So if we divided both sides by 3, then we would end up with 5 minus I times x2 is the same as 2x1, which means that our eigenvector then says, well, x1 would have to be 5 minus I, and x2 would have to be 2 for these to be the same thing. So we have 5 minus I times x2, which is 2, has to be 2 times x1, which has to be 5 minus I. And then we have to find our general solution, right? Which is our y is equal to C1u plus C2v. All right, then let's take y1. Our first solution then is 5 minus I, 2, e to the 1 plus 3I times t, which we'll rewrite into 5 minus I and 2, and this will be e to the t again, and now it'll be cosine 3t plus I sine 3t. Which means now when we start distributing the 5 minus I, we have to distribute. So we'll have 5 times each term, so we'll get 5 cosine of 3t plus I times 5 sine of 3t. And then we have a minus I times cosine 3t and I sine 3t. So minus I cosine of 3t, and then minus I squared, I'll write it up, and then sine of 3t. The second one is much easier, just 2 cosine 3t, and then plus I times 2. Sorry for the barking dog. She's just a puppy. I times 2, and then sine 3t. And then this guy's all going to be times e to the t. So if we were to go through and highlight this again, let's find our complex will be here. It's not the I squared, it's here and here and here. And our real part here, here, and that I squared is going to become a negative 1. So if we were to separate these guys out, we end up then with the real part, so 5 cosine of 3t, and then minus an I squared is minus negative 1, so plus sine of 3t. And in the second row, we just have the 2 cosine of 3t. This is all times e to the t, right? And then plus I have an I, and then all of this will be 5 sine 3t minus cosine 3t, and just 2 sine of 3t. And all that is also times e to the t. This is u, and this minus the I is v. So our general solution, y, is c1, and I'm going to put the e to the t in the front again, and then our 5 cosine of 3t plus our sine of 3t and our 2 cosine of 3t plus c2 e to the t and our 5 sine of 3t minus cosine of 3t and our 2 sine of 3t. And that is our general solution here. That's our general solution. And for our final example from section 10.6, we want to find the general solution of y prime is equal to 3, negative 9, 4, negative 3 times y, and this time we have an initial condition. We have a y of 0 is equal to 2 and negative 4. So Let's see how we're going to go about doing this guy. First things first, find our eigenvalues. All right, so we end up with the determinant of 3 minus lambda, -9, 4, and -3 minus lambda. So we get the characteristic equation 3 minus lambda times -3 minus lambda plus 36 equals 0. So -9 plus 3 lambda minus 3 lambda plus lambda squared plus 36 equals 0. So we get lambda squared plus 27 equals 0. Or lambda equals plus or minus 3 root 3, or 3I root 3. Almost forgot the I because we have lambda squared equals -27. So lambda is plus or minus 3i root 3. 9 times 3 is 27, so that's why it's 3i root 3. And remember the I here, I'll make it a little bit clearer there. I is our square root of -1. So step 2, we got to find our associated eigenvector. All right, then we've got 3 minus 3i root 3 and 4. And then we've got -9, -3 minus the 3i root 3, which is actually a little bit simpler than it looks because we don't really even need the parentheses, and 0, 0. So probably the easiest thing to do here is to look at the first row, and again, we're going to be able to factor out a 3. So we have 3 minus 3i root 3 x1 minus 9x2 equals 0. And that means if we factor out a 3, we get 3 times 1 minus I root 3 here. x1 equals 9x2. And now we can divide both sides by 3. And 1 minus I root 3 x1 is equal to 3x2. Scroll up a little here, and that means that our eigenvector is, well, x1 is going to be 3, x2 is going to be 1 minus I root 3. And there's our eigenvector. And again, it's just figuring out what makes the each side equal the other. So we have a 3 and a 1 minus I root 3. All right, now we got to find our general solution, which is our y being c1u plus c2v. So let's do that. So for y1, we have 3 and 1 minus I root 3 times e to the 3I root 3 times t. Right? There was no a plus bi here, or alpha plus beta I. For this one, we only have the beta I. So there's not going to be an e part of this Euler. This is only going to be 3, 1 minus I root 3, and this is simply going to be cosine of 3 root 3 t plus I times the sine of 3 root 3 t, which is a little different than what we're used to seeing, but that's okay. We'll handle it. It'll be okay. So let's see here. If we start splitting this up by factoring things out, simplifying, and then separating them into real and complex, let's see what we end up with. So just a 3. So 3 cosine 3 root 3t plus I times 3 sine of 3 root 3t. That's the easy one. So now let's do the distribution we have to do with the 1 and the negative I root 3. So 1 is easy, just leave what's there there. Cosine of 3 root 3 t plus I sine of 3 root 3 t. And now we have a negative I root 3 to multiply by everything. So negative I root 3 cosine of 3 root 3 t, and a negative I times an I is going to give me a negative I squared root 3 sine of 3 root 3 t. And we don't have any e here, so that's it. And so when we start putting this together with the complex, right, and our real parts, then we find out that our general solution here is C1, real parts, so 3 cosine of 3 root 3t on the numerator, or the first, not the numerator, this is a matrix. So in the first row, in the second row, we'll have a cosine of 3 root 3t. And then minus an I squared is going to be minus a negative 1, so plus a root 3 sine of 3 root 3t. And that is y1 plus c2 times our complex part, which would give us 3 sine of 3 root 3t in the first row. Second row is going to give us sine of 3 root 3t minus root 3 cosine of 3 root 3t. So it looks a little bit different than what we're used to because it doesn't have an e, but that's okay. And now we need to apply our initial condition. So we have to apply that y of 0 is the vector 2, negative 4. So if that's the case here, then we get 2, negative 4 is equal to, right, C1 cosine of 0, right? So it's equal to C1, and now this is going to be 3 times the cosine of 0 is just 3. Cosine of 0 is 1, plus root 3 times the sine of 0 is 0, so it's just 3, 1. Okay, and then plus C2, sine of 0 is 0, sine of 0 is 0, so then we get negative root 3 times cosine of 0 is 1. So we end up with a system now that says I have 2 is equal to 3c1 plus no c2, and we have negative 4 is equal to c1 minus root 3 c2. So we could rewrite this as the system 3, 0, 1, negative root 3 times c1, c2 is now equal to 2 and negative 4. And already we know that 3c1 equals 2, so we can find c1 already. That's kind of the nice thing. So we don't really have to do a whole lot. We could just say 3c1 is equal to 2, so c1 is 2/3. And that means that c1 minus root 3 c2 is equal to negative 4, which means negative root 3 c2 is going to be negative 4 minus 2/3. If we subtract over the c1, or we get c2 is going to be negative 14 over 3 times the negative root 3, so it would be negative 14 over negative 3 root 3, which is 14 root 3 over 9. Just by rationalizing the denominator, let me make it a little neater for you. So it would be positive 14 root 3 over 3 times 3, which is 9. Which means then our final solution is that y is equal to 2/3. And then we have 3 cosine of 3 root 3t. We have cosine of 3 root 3t plus root 3 sine of 3 root 3t. And then plus 14 root 3 over 9. And we had 3 sine of 3 root 3t. And sine of 3 root 3t minus root 3 cosine of 3 root 3t. And that is our general solution here. So when we have an initial condition, just like all of our other ODEs, you don't put it in until the end and you use it to solve for C1 and C2. I have a couple of problems listed on the next slide, and just make sure that you're checking the posted written homework to know which ones to do. So here are problems 3 and 17 for practice, and again, check the posted written homework assignment to see which problem or problems you're supposed to do of these two.